Next, let us learn the foundations of how data is organized. Spotify has over 100 million songs. Yet when you type a song name, results appear almost instantly. It's not just because of powerful servers. Organize data differently. Searches take minutes or hours. The difference is structure. Data organization dictates app speed. See this in action. Two Spotify versions. One, an unsorted list. The other, a hash table. Both have 100 million songs. You search for Bohemian Rhapsody. In the unsorted list, Spotify checks each song one by one. On average, the system must examine roughly half the collection before finding the result. With 100 million songs, that's about 50 million checks. That's the hidden cost of poor organization. But in the hash table version, Spotify jumps directly to the song in one step. Instead of searching through songs, it calculates where the song should be stored. That calculation acts like a shortcut address. Same data, different organization. Yet the work performed by the computer collapses from tens of millions of checks to essentially one step. That's the power of choosing the right data structure. They aren't just academic diagrams in textbooks. They determine whether software feels instant or frustrating. By the end of this video, you'll understand why some structures make operations lightning fast and others unbearably slow. You'll learn how engineers think about performance before they write code, how different structures solve different problems, and how to choose the right one instead of guessing. Data structures can seem overwhelming, but most of them can be understood using two simple dimensions. Data structures fall into two main categories. First, linear versus nonlinear. Second dimension, static versus dynamic sizing. Linear structures form a single path, like a train track. You visit items one by one. Think of an array. Static structures have a fixed size, like a reserved parking lot. They're fast and predictable. The trade-off is rigidity. Space must usually be reserved in advance, even if some of it remains unused. Or a linked list. Dynamic structures grow as needed, like an expandable backpack. Every node knows where the next node lives. That flexibility allows the structure to grow naturally over time. The downside is that nodes may be scattered throughout memory, making traversal less efficient than an array. Nonlinear structures branch out, like a family tree. You can jump between paths and explore multiple directions. This mirrors how information is organized in the real world. Folders, product catalogs, company structures, and recommendation systems all naturally branch. This is a dynamic tree capable of expanding as new data arrives. Modern applications rarely know their final size in advance, which is why dynamic structures are so common. Spotify uses both dimensions. A playlist might use a static array or a dynamic linked list. Genre catalog forms a tree, nonlinear and hierarchical. Understanding these two axes helps match structure to problem. Now let's talk about Big O. This topic often intimidates beginners because it looks mathematical. But Big O isn't really about math. It's about this question. If I double my data, how much longer does my operation take? It's about growth rate, not absolute speed. O of 1 means constant time. Same time, no matter how much data. Finding a song in a hash table is O of 1. Whether 100 songs or 100 million, it's one step. Growth happens in the data, not in the work required. O of n means linear time. Double the data. Operation takes twice as long. Searching an unsorted list is O of n. 1 million songs. Check up to 1 million. 2 million. Check up to 2 million. Linear time isn't bad. In fact, many useful operations are linear. The key insight is predictability. O of n squared means quadratic time. Double the data, operation takes 4 times as long. Comparing every song to every other song is O of n squared. With 1000 songs, that's 1 million comparisons. 2000. 4 million. As data grows, O of n squared becomes unusable. This is where the trouble begins. Every new item interacts with every other item, and small datasets hide the problem. Notice that all three operations might appear fast when the dataset is tiny. That's why Big O focuses on growth. At Spotify scale, the differences stop being theoretical. Fractions of a second become seconds. Seconds become hours. Suddenly the choice of data structure becomes the difference between a usable product and a failed feature. Engineers don't obsess over Big O because they enjoy mathematics. They care because scaling problems are expensive. A design that works for 1000 users may fail for 1 million. Every data structure has hidden costs. Let's see them in action. First, dynamic resizing. A dynamic array grows as you add elements. But when it runs out of space, it has to pause, allocate a larger block of memory, and copy every single element to the new space. That's expensive. A linked list doesn't have this problem. It just adds a new node without disruption. But linked lists use more memory per element, because each node stores a pointer to the next one. Notice that nothing useful is happening during this copy operation. The application is spending time moving data rather than serving users. These pauses are infrequent, but when they occur, they can create noticeable performance spikes. In linked lists, the extra pointer may seem small, but multiplied across millions of elements, the memory overhead becomes significant. Faster insertion isn't free. Second, hash table collisions. Hash tables are fast because they map keys directly to buckets. But when two keys hash to the same bucket, you get a collision, and the lookup slows down. You have to check multiple items in that bucket, turning O of 1 into something closer to O of n in the worst case. Good hash functions spread data evenly across buckets. Most of the time, collisions are rare, but understanding collisions is important. Spotify's queue uses a linked list because users constantly add and remove songs. Resizing an array mid-playback would cause stuttering. Spotify's search uses a hash table because lookups need to be instant, and collisions are rare with a good hash function. Understanding these trade-offs helps you avoid performance cliffs. Engineers rarely ask which structure is best. Instead, they ask, best for what? Choose the right data structure. Follow this framework. First, identify your bottleneck operation. Is it search, insert, delete, or maintaining order? Optimize for it. Second, estimate data growth. Is it fixed size or dynamic? Static structures are predictable. Dynamic are flexible. Third, determine relationships. Is it flat or hierarchical? Linear structures are simple. Nonlinear are complex. Fourth, choose a structure where your bottleneck has the best Big O. If you search 1 million times but insert 10 times, optimize for search speed. Accept trade-offs. No structure is best at everything. The names of the structures change, but the decision process remains remarkably similar. Spotify uses hash tables for search. Lookups are the bottleneck. Linked lists for queues. Dynamic insertion matters more than direct access. Trees for genre hierarchies. Relationships are inherent. Notice how every choice follows the framework we just discussed. Start with the bottleneck, then choose the structure that makes that bottleneck efficient. Every choice involves trade-offs. Optimizing for one aspect means sacrificing another. Understand these to choose wisely. There is no perfect data structure, and every structure specializes in solving a particular class of problems. Google, Facebook, banking systems. They all depend on choosing the right structure. At internet scale, even tiny inefficiencies become expensive. A few extra milliseconds multiplied across billions of operations can translate into enormous infrastructure costs and poor user experiences. The right structure isn't the fanciest. It's the one that matches your problem. Great engineers are effective because they understand trade-offs and choose deliberately. Master this mindset, and you'll build systems that remain fast, reliable, and scalable long after the data grows beyond what you originally imagined.